Taking a look at 4.4, graphing and modeling with quadratic equations now. Sorry, quadratic functions. With this first beginning piece, they have us checking based off of the parabola seen here with your friend and you tossing a ball back and forth. You toss and catch the ball at waist level, 3 feet high. What equation in standard form models the path of the ball? Well, let's start off by saying that these two are actually pretty small if we think about this, or no. No, their waist is about 3 feet, so they're actually sized pretty normally. What would the vertex be if we had to model the path of the parabola? Well, let's say that our axis of symmetry is seen here. If this is 5 feet away, so half of the distance between, but 6 feet up, we would say the parabola would be 5, 6 as far as going from the ground. So from the ground. But if we're talking waist level, this would be 5, 3, because it's 3 units up. Because from waist level, it's 3 feet high. So you can do 5, 6 from the ground or 5, 3 from waist. If we take this further, how can we model this path of the parabola with the vertex that we found above? Well, we know that we have that vertex, the model of that is going up and above. We see two parabolas here. So what equation in standard form models the path of the ball? Well, we know that if we're going for the vertex of 5, 3, there's some a coefficient. We know that we're deducting 5. This is squared. And we're then adding on 3. We don't necessarily know what the a coefficient is, and this is kind of an issue that we come across in this section because we're just given points. So we know that, let's call this 0, 0 and 10, 0. So it's as if we do have some points in between here. So if we want to mark this up, 0, 0. We also have 5, 3. We also have 10, 0. It would be tricky to try and navigate what this is going to be. And we'll talk about how we can get a hold of that. So we know that there's some a coefficient we don't know, and we'll see in the problems here that we can solve that. So when we know the vertex and a point on the parabola, we can use vertex form to write an equation of the parabola. If we don't know the vertex, we can use standard form and any 3 points of the parabola to find the equation, which is interesting because we do have 3 here. The points cannot be, as long as the points are not collinear, 2 of which are in line vertically, one's just going to have to be on the graph with exactly that one quadratic function. So this does get tricky. There are a lot of steps here, so we'll see what we can do. Because we have these 3 points, and we're being asked to find the equation in standard form, where again, this is ax squared plus bx plus c. And they're kind of nice to us in a sense because they hand us a really crucial point. So if we look at these points, what's one point that we can really use to our advantage here? Well, we know that if x is 0, the outcome is the y-intercept. So we know that for this is going to be c. So we can already start to frame this equation. So we'll have x squared with some coefficient, some b term, and x. But collectively, our y-intercept 0. So that's on the right track. And so now our goal is to try and end up with a b term and an a term. So let's make a note of that. So the goal is to find a and b. We know that we have 2 points that are on the line. So if we plug these in, so we're plugging in 2 points. I know that if x is -1, the outcome's 1. So if we plug that in accordingly here, we know that we have a multiplying with -1 squared plus b times -1. We know that's c0, so we don't have to write that. So that's for that first point. The second point, 1, 5. If a is 1, x is 1. Sorry, if a is something we don't know, but we add on the rest of it. This should all be equal to 1. This should all be equal to 5. So we're still trying to find a and b. We know that this is going to satisfy this type of equation because we're using points that are definitely on the line. So if we simplify this further, hopefully we can say that -1 squared is just 1, so this is just going to be a. We can then deduct b. Here, 1 squared times a is just a, adding on b. So what I did here was just evaluate the terms being squared and simplifying with the coefficients. So if we really focus on this problem seen here, what kind of problem does this look like? It kind of looks like a system of equations, which we've seen previously in the review. We saw that we could use substitution, we could use elimination. In this case, elimination looks as if it's the easiest because we have opposite b terms. So we're going to eliminate. This will eventually leave us with a terms. So if we combine everything, 1 and 5 gets us 6, a and a gets us 2a, b's canceled. So this is now going to say 6 equals 2a. If we divide by 2, we know that our a coefficient is definitely going to be 3. And it's kind of a wild ride how we can say all of this, but it totally makes sense logistically how we got here. I think the trickiest part where I see students trip up is breaking this down. So I know that a is 3. How can we get a hold of b? Half of our goal's done. How can we get b? Well, we have some options here. We have some equations seen here that we know have to equal a certain number. So you have some options with how you can go about going for the rest of this. So you could take into account that we have those two equations. So this is to find the b coordinate. We know that it's 3x squared plus some number with x, then adding on 0. Not too picky on which equation which point you use, as long as it's not 0, 0, because this will just fall apart at that point. So for this one, I'll choose when x is 1. So if x equals 1, I know that it's 3 times 1 squared plus b times 1 plus 0 equals 5. So I'm using point 1, 5 to get b. So when I simplify this, 3 times 1 squared is 3. Adding on b plus 0 equals 5. Solving for b by deducting 3 on both sides. B is equal to 2. So if b is 2, we're adding on 2 here. We can simplify this equation to 3x squared plus 2x. Then we're done.